In the last video we derived a formula for the curvature of a curve. Let's take the example y equals x squared. So here's the formula for the curvature. That's called kappa. We need the first and second derivatives. The first derivative is 2x, the second derivative is 2, so we just plug these into this formula. Now, the curvature involves taking a magnitude, but since 1 plus 4x squared is positive for all values of x, we can just drop these magnitude lines. Let's look at a graph of the curvature. Well, we see that as x tends towards plus infinity, the denominator blows up, so kappa will go to 0. So the x-axis is a horizontal asymptote for this function. Similarly, if x tends towards negative infinity, well, x squared is going to blow up and the denominator will go off to infinity. We see that kappa is going to approach 0. And we see that kappa is positive for all values of x. So the curvature approaches x for x tending towards both positive and negative infinity. We see that this function is symmetrical about 0 because say for example x is 1. Well, we will get the same value for the curvature at x equals 1 as we will for x equals minus 1, because 1 squared is the same as minus 1 squared. So we have an even function. At x equals 0 we get kappa equals 2. So the curvature is greatest at x equals 0. So here is y equals x squared, and you can see quite clearly the curvature is greatest here, and it's the same of course for points equidistant from the origin on either side, because the y equals x squared is symmetric about the y-axis. As x goes on and on, the curvature gets less and less for large positive x as well as large negative x. Let's take this example here. Now this is the equation of a circle centered at the origin with radius of a. So such circles have an equation of this form. So this is what we get when we make y the subject. So we need to get y as a function of x, so that's our f of x. So to get the curvature we need the first and second derivatives. So to get the first derivative we take the half in front and subtract 1 from the power. So we'll get a half a squared minus x squared to the power of minus half. So we can take that down and write it as a half a squared minus x squared to the power of plus a half. Then we differentiate what's inside to get minus 2x. So we'll have minus 2x on top and a half into a squared minus x squared to the half underneath. The 2's cancel out, so we get this result here. Now let's differentiate this again. So we have a quotient here, so we take what's underneath, a squared minus x squared to the power of a half, and multiply by the derivative of what's on top. The derivative of minus x is minus 1. Then we subtract from that the function on top, which is minus x, times the derivative of the function that's underneath. So we have to apply the chain rule to what's underneath. So we take the power down, take 1 from the power, then we differentiate what's inside the brackets. Differentiate a squared minus x squared, we get minus 2x, because a is a constant. And we divide everything by v squared. So we take a squared minus x squared to the power of a half and square it. That'll give us a squared minus x squared. So that's just a formula, v du dx minus u dv dx all over v squared. Now I will multiply everything on top by a squared minus x squared to the power of a half. So when I multiply this by a squared minus x squared to the power of a half, I just get a squared minus x squared. And that's multiplied by minus 1. Well, I'll just do that multiplication now. So we get x squared minus a squared. Okay, now I multiply this here by a squared minus x squared to the power of minus half. That'll give us a squared minus x squared to the power of 0, which is just 1. So we will have minus minus x, that's plus x by a half, by minus 2x. So these 2's cancel out and we get minus x squared there, which would actually cancel with the plus x squared. Now I have to multiply underneath by this quantity here, so that's going to give me a squared minus x squared to the power of 1 plus a half, or 3 halves. So we do indeed get this result Okay, so now for the formula we need 1 plus f prime of x squared. Okay, so just let's see the formula again. We need 1 plus f prime of x squared in the denominator. So here's f prime of x. We need to square this. We get x squared on top. We square what's underneath. We get rid of that half. We need to add 1 to it. And if we have a common denominator of a squared minus x squared, we will have a squared minus x squared plus x squared on top. That's a squared. So this should be a squared here. On top we have f double prime of x. So this goes in on top. Now on top and on the bottom we have a squared minus x squared to the power of 3 halves, so that cancels out. Then we have minus a squared divided by a squared to the power of 3 halves. Well, a squared to the power of 3 halves is a to the power of 3. So we have minus a squared over a cubed. That's minus 1 over a. So we have the magnitude of minus 1 over a, which is plus 1 over a. Now a is the radius of the circle. It's a constant. So we can see that the curvature is constant. So x disappeared out of this. So the curvature doesn't depend on x. The curvature is the same everywhere, as we saw in the previous video. And its value is 1 over the radius. So if we double the radius of the circle, we halve the curvature. So the bigger the radius, the smaller the curvature, and vice versa. That's something that we saw in the previous video. Now let's look at the curvature for parametrically defined curves. So point on the curve is given in terms of the parameter t. So x is given as a function of t and y is given as a function of t. Now for the formula we need f prime of x, or dy dx. So we need, that's using this Cartesian form here. So we can get dy dx from dy dt and dt dx by multiplying these two derivatives together. You can see the dt's go out, so they behave like that. And we can write that as dy dt divided by dx dt. Just invert this one. But dy dt can also be written y dot, and dx dt can be written x dot. So the dot indicates we're differentiating with respect to time. Now for the formula we need f double prime of x, or d2y dx2. So we need to use the quotient rule to differentiate this. So we take the function that's underneath in the quotient, that's x dot, and multiply it by the derivative of what's on top. So we're differentiating with respect to x, and then we have a minus sign. Take what's on top, which is y dot, and multiply it by the derivative of what's underneath. So we have to differentiate x dot with respect to x, and then we divide the whole lot by v squared. Well, x dot is v. Now we can write dy dot dx as dy dot dt times dt dx, and that's the same as dy dot dt divided by dx dt. Similarly, we can write dx dot dt as dx dot dt, sorry, dx dot dx as dx dot dt divided by dx dt. The dt's will cancel. But the derivative of y dot with respect to time is written dot dot y, and the derivative of x with respect to t is written x dot. So I've just plugged in for those derivatives, dy dot dx and dx dot dx. Finally, we can divide above and below by x dot. So we divide everything on top by x dot, gets rid of those x dots, and then we divide underneath. I'm sorry here, we have y double dot divided by x dot, and we have x double dot divided by x dot. So this is what we get, and we multiply above and below by x dot. So that those x dots cancel out on top, and we get x dot y double dot minus y dot x double dot on top, and underneath we have x dot squared by x dot, that's x dot cubed. So that's our second derivative, and that's what goes on top for our formula. So the x dot cubed is taken down underneath and it's multiplied by 1 plus f dash x squared to the power of 3 halves. So we have 1 plus this here squared to the power of 3 halves. We can write x dot cubed as x dot squared to the power of 3 halves, because 2 times 3 halves gives us 3, and since it has the same power as the thing in the square brackets, we can multiply the x dot squared into the what's inside the square brackets. X dot squared by 1 and then we have x dot squared by y dot squared over x dot squared, so the x dot squareds will cancel there in the denominator. And the whole lot is to the power of 3 halves. So that's our formula for the curvature of a curve defined parametrically. Let's take an ellipse. So here are the parametric equations for an ellipse. So to get the curvature we need x dot, y dot, x double dot and y double dot to plug into this formula. The derivative of the cos function is minus sine. The derivative of the sine function is cos. And we can similarly get the second derivatives, plug them all in here. We have x dot times y double dot, that's plus 2 sine squared theta. We have y dot times x double dot, that's and then we have a minus sign, so minus minus are plus 2 cos squared theta t. Now sine squared t plus cos squared t is equal to 1, so we just have 2 times 1 or 2 on top. Then we have x dot squared plus y dot squared, so we have 4 sine squared t plus cos squared t raised to the power of 3 halves in the denominator. Now if we look at this denominator here, what's inside the square brackets, we can replace cos squared t with 1 minus sine squared t using an identity. Cos squared t plus sine squared t equals 1. And you see we get 4 minus 1 or 3 sine squared theta and then plus 1. Now t runs from 0 to 2 pi. If we want to generate this curve, which is an ellipse, let's consider maximum and minimum values for the value of kappa. To get the minimum value of kappa, we must maximize the denominator. Now the maximum value that the sine function can take on is plus 1. And sine of t is plus 1 when t is pi over 2 or 90 degrees. When t is pi over 2, x is 0 because the cos of pi over 2 is 0, but y is equal to 1, so we have the point with coordinate 0, 1. So that's this point here of the ellipse. So at this point we have the minimum value of kappa, and that looks plausible. Tangents to the curve are not turning, that are turning slowly for values of x in this neighborhood, about 0. To get the maximum value of kappa, we need to minimize the denominator. Now the minimum value that sine of t can have is 0, while the minimum value of the magnitude of sine of t is 0, or the sine squared of t is 0. That occurs when t equals 0, then kappa equals 2 divided by 1. So the maximum value of kappa is 2. Now when t is 0, if we go back to the equations of the curve, we have 2 cos 0, which is 2, and the sine of 0 is 1. So 2 comma 0 is the point on the curve that gives us the maximum value of kappa. So the curve is turning much more quickly here, much more sharply at x equals 2.